Okay, now to go through to the part 2 of that rectangular waveguide calculation and this experiment, that is the TM modes. That's very much that's the same type steps as required in the obtained field solution, the TE modes. So after calculating this, we found that there is a k constant in beta g. Beta g means that is the propagation constant. If k is greater than kc, that is the real value and is indeed traveling in the plus z direction. If it is less than kc, that's imaginary, and that means the propagation mode decays rapidly with distance z in the plus z direction. So after calculating in long run, we will get this, that is the cutoff frequency equation. If you know the mn, that means if it is TE or TM, it's the T mode or TM mode. If there is an mn means mn. If the value of m is 1, n is 0, you can put the value here with the m parameter and n parameter, and then just you know the what can I say, the dimension of rectangular waveguide, the length and the breadth of rectangular waveguide. You can easily find out the cutoff frequency. After that, you can easily find out the what can I say, that is the cutoff wavelength. Again, so after calculating this, we go through to the wavelength in the rectangular waveguide. That is the wavelength in the rectangular waveguide, lambda g, that is the guide wavelength. Okay, and that has been derived through the cutoff wavelength. And if you know the operating wavelength and the cutoff wavelength, we can find out the guide wavelength through this equation. Okay, so there are a lot of derivations out there. Okay, and that is the phase velocity. The phase velocity, or the velocity of a constant phase point in waveguide, is looks like that. Vp is equal to f lambda g, and you should take the speed as phase velocity waveguide can exceed the speed of light in free space, which is 3 × 10⁻⁸ meter per second. That means its phase velocity is quite equal to the velocity of light. So that is the experimental setup or experimental procedure of rectangular waveguide to find out the modes and its characteristics. So the setup equipment is like that, same thing that we have learned from the first experiment, the setup of the Garn oscillator, because Garn oscillator after oscillating, it produces the microwave frequency. Okay, that is one kind of the voltage supply of electrical circuit. We know that's been compared to in microwave engineering, that has been compared to like that the supply voltage of a circuit. So go through to the power supply, connect to the Garn oscillator. The Garn oscillator will just generate the microwave frequency and microwave energy with microwave frequency also. There is a square wave generator with the PIN diode modulator. That means that is a complete package of what you can say, that is just like communication block diagram setup. You need to have a modulator, then the modulator goes to the variable attenuator. That means variable attenuator is like that, just like a channel that go through to it. Okay, and the variable attenuator you can imagine, or you can just analogy with the resistance of the circuit, or inductance of a circuit, or capacitance, or any kind of impedance of a circuit. So there will be a variable attenuator, and the frequency meter was also connected to find out the frequency, and there is a slotted line. Okay, what are the slotted lines? To find out the SWR, or you can say the standing wave ratio indicator, that has been connected to the slotted line, and then it should have to be connected to the straight waveguide, and there will be a reflecting sheet. Okay, so why we are giving the reflecting sheet? You just imagine with the transmission line theory. Excuse me. Just imagine in the transmission line theory, there is an incident wave and there is the reflected wave, and you have to find out the if you know the reflected wave and the incident wave of certain kind of, what you can say, that certain waveguide or transmission line or microwave energy that go through to it. So you can find out the reflection coefficient and the transmission coefficient. And if you know the reflection coefficient, you can easily find out SWR, that means standing wave ratio. Okay. So when an incident wave go through to the straight waveguide, there are slotted lines. Slotted lines means you can control the wave that go through to the slotted line. Okay, because there are the variable or attenuator after going through to the magnetic after going through to the variable attenuator. When it go through to the slotted line, there will be uh, the slotted line is one kind of device that can be used as a variable of the flow of the microwave energy. So after going through to the straight waveguide, it will go to the reflecting sheet. So apply voltage to the gun oscillator. Also apply 1 kilohertz to the 2 volt peak to peak square wave to the PIN modulator. Adjust the variable attenuator to 10 decibel. Set the SWR meter such that the meter indicates approximately the middle of the scale, and adjust the frequency of the square wave generator so that the SWR indication is maximized. Turn the frequency meter until there is a significant drop on the SWR indicator. Record the frequency in table and detune the frequency meter. The second is the frequency measurement. The second measurement is a measurement of the free space waveguide wavelength and guide wavelength. When the reflecting sheet is moved toward the open and end of the waveguide, with the reflecting sheet oriented to the waveguide with right angle, then the standing wave pattern should vary due to the reflections from the plate. The variance of standing wave is detected by the probe in the slotted line. Find two adjacent positions where the two detected values are minimum. The slotted line is one kind of detector. Okay, there's a bypass detectors, two-sided detectors. As you can see, go through to that part of wave through slotted line, and there are some reflecting wave from the reflecting sheet. The slotted line measures these two incidents. Okay, and as you can see that that is the okay half wave. The distance between the 2 points corresponds to the half wavelength in free space. That means to find out the maxima and minima. Then cover the output of the slotted line with the sorting plate. Vary the slotted line and locate a position where the detected output voltage is minimum. From that point, find another adjacent point where minimum is detected again. The distance between two points is the half of the guide wavelength. Record the value, that is the frequency. That is measured lambda g, calculated lambda g. Then we have to find out the wavelength through that with different frequencies and compare it to it. So that is the end of the third experiment. That is our table that we have to fill it out. So just change the frequency and we will get the measured lambda g and calculated lambda g by calculation. Thanks for being with me in that part. We will go to the next laboratory experiment.